If you click this video at one point away, then please tell me what the reason was so that I can improve. Otherwise, hi and welcome. I am trying to learn electrical engineering today, alternative current, and after we've done with, we're gonna do extensor carpi on our strength training that lies here. And if you participate in the extensor carpi on our strength training, then it's at your own risk. Alternating current. We have now found out that an induced current cannot be created unless movement is occurring. I didn't really understand what an induced current is, but the movement of the magnet inside of the coil is important. That is the whole reason why it is necessary to have fire plants or something else running, because with these coal plants there's water heated, but the water has, because it's heating, it's expanding and it's moving or something, and now it pushes against something and that turns the thing around. So it pushes like a wheel of a mill against it, and now it turns it. And that turning thing turns the magnet inside of a wire of coil. And that is the whole reason why we're doing that. So that whole big thing with the digging the coal up from the ground and burning it is to heat the water, to have water pressing against the blades to move that thing, which then turns the magnet inside of a coil of wires. And if such a magnet turns inside of a coil of wires, don't really understand it, then electricity is generated. And what we're here saying is, we found now out that an induced current cannot be created unless movement is occurring. This current can only be created if something is moving. If a permanent magnet is used, it must be moved with respect to the conductor in which the induced current is required to flow. If a current is used as so-called primary current to set up an induced current in another coil called a secondary coil, the induced current only flows when the primary current starts or stops. The starting and stopping of a current is not instantaneous. There is a small period of time during which a current grows to its maximum value and then grows less. There are two things which I can say to it. The third thing first, I don't understand it. The other two things, there was something I was wondering, how's now the current produced? They said it is at one point, I think, that there is a current running through the coil wire around the magnet in the middle. Or is it just the metal and the magnet? So maybe they're talking about that there has to be first a current on the coil to keep the magnet in the middle and then creating the current. And the other thing was that the lines of this magnetic field, which is just generated if there is a current flowing, are never crossed. If you put two magnets together, they are repelling. If you put them to the side, they're doing basically nothing. If you put them to the other side, they are attracting each other. Basically, similar to that, a coil, a wire under electricity has around an electric field. We had it in the previous part. I'm trying to puzzle together what you understood, maybe you're watching also. So an electric field around them. And these electric fields never cross each other. If they do, there was something funny happening, which was important. It was explained here. We can just read it again. I don't know what is explained here. So these two things can I say to that. And the first one, I don't understand it. During this period of time, the magnetic field associated with the current also grows and decays. It is this movement of the magnetic field which is capable of establishing an induced current. Now I don't know what induced current means. I'm even not so much in usage with the word induced. Obviously, what is wanted for practical purpose here is a current which starts and stops many times a second. Such a current is called an alternating current. Usually, such a current has the form of a sine wave. The current flows first in one direction, growing to a maximum value, then decays to zero before growing to a maximum in the opposite direction. The current goes to and fro, and such a current is what is required for a transformator which involves electromagnetic induction. I don't know what induction is. I don't understand it, but electromagnetic induction. Michael Faraday, whose skill as an experimenter. So basically, we are through with the part to alternating current. We just don't understand it, so I'm going to read the last part again. Michael Faraday, whose skill as an experimenter led him to many new discoveries in physics, investigated the phenomenon of electromagnetic induction using an iron ring, supposedly an anchor ring, as a continuous core for two coils of wire. We have already discussed the advantage of providing a closed circuit to avoid the creation of free poles in an electromagnetic circuit. The circuit used was that shown. The wire, of course, was insulated so that no current from the battery passed through the iron ring coil from A to B. You should set up some familiar form of apparatus in the laboratory. Okay, let's see that. When the switch is open, most require the use of when the switch is closed on one, so on one comes the current in and goes from at the side of the coil through to the other side. And there's somehow something happening on the other side. When the switch is closed and the current flows in the coil A, a current flows in coil B. They have in the middle the string. So here's the coil 1 entangled around the part of that coil of the thing in the middle, entangled on one side. And there's the other one entangled on it. And if that switch is on, something happening on the other side. The meter shows a deflection, say to the right. Once the current is stopped steadily in coil A, the current flows in B. The meter shows this by returning to the zero reading. When the switch is opened again, thus stopping the current flowing in coil A, again there will be observed a pulse of current in coil B, this time moving the meter to the left. The currents caused to flow in coil B are called induced currents, and the phenomenon itself is called electromagnetic induction. This occurs whenever the current starts or stops. But why? Faraday's experiment involves, of course, the basic principle involved in the transformer, which will be considered in a later unit in the series. You should now perform further experiments to supply more information on the rather puzzling starting and stopping aspect of an induced current. You will need a coil of many turns of wire, 100 or more, connected to a sensitive galvanometer. Investigate the effect of moving a bar magnet into and out of the coil as shown. You should then find the effect of moving the magnet more quickly. Additionally, you should try the effect of holding two bar magnets side by side, so that you have in effect a magnet with twice the pole strength. You will find that all these variations will give you a great deal of information to consider. First, whenever a conductor is cutting that is moving across magnetic lines of force, a current flows in the conductor and the circuit containing the conductor. So these magnetic lines of force are crossed, and then a current is flowing into the other circuit. But how, why, what? The direction of the induced current is always such as to oppose the cause producing it. No, I don't really understand that. One other thing where we're going to go back to. You will already know that iron is more permeable to magnetic lines of force than air. It is easier for a line of force to pass through magnetic materials to permeate them than it is for these lines to pass through non-magnetic materials. This can be illustrated simply by using iron fillings to show the field existing between two unlike poles, and the alternation in the field when a piece of soft iron is placed between the poles. The lines of force crowd into the piece of iron. For this reason, an electromagnet is usually provided with a soft iron core. If you consider two such electromagnets, the electromagnet with a straight bar of soft iron as a core is not very efficient, as one of the two induced poles is not being put to use. The magnet with a horseshoe iron core, that is what I'm talking about. Let's see. I'm not able to explain it, but I can grasp it. There is a magnetic field. If you have a bar and the electric current and a wire around it, when there's something current let through, and now the magnetic field goes out to the outsides of both sides. If you take now this bar and bend it to a horseshoe and bend the bar, the magnetic force currents going out to the side, out to the bottom, and not just to the side. And if you have them now like that, there's no magnetic field at these two ends, and there you can put something and you can lift it up with that magnet like that. That is the first thing. And the other thing, there's a piece of soft iron. I don't understand it. The magnet with a horseshoe iron core is able to create a closed magnetic circuit. So that's the first thing. Okay, the thing with the bending, and when we're having the output of a magnetic field at the both ends together, then you can use both. That is all the lines of force traveling either the core or the piece of material being lifted. You should note that the closed circuit is a magnet insofar as magnetic lines of force exist in it, but there are really no free poles, as at no end do the lines of force leave the magnetic material to pass into the air. Okay, does it help us? Let's just read it again. Alternating current. We have now found out that an induced current cannot be created unless movement is occurring. So we're saying off and on, off and on. It has to be switched on and off. Otherwise nothing is happening. And in the moment this is switched on, then a current is induced. So we understood now what we're talking about. We don't understand why and what, but we understand what we're talking about. If a permanent magnet is used, it must be moved with respect to the conductor in which the induced current is required to flow. The turning magnet inside the generating thing of our big generator machine is every time it's moving around, shifting the electromagnetic field, and every time the magnetic field of a magnet is turning, it scraps along the other one, passes the lines, switches us on and off, and electricity is generated. The magnet has a magnetic field with all these lines of force around it, which never cross. If you turn it now, these magnetic fields are crossing the magnetic field of a current around. I don't get it, but you turn it and these magnetic lines of fields are crossing every time the magnet is turned once this thing, and every time that thing in the generator or whatever turns, line of force is switched and then electricity is generated. If a permanent magnet is used, it must be moved with respect to the conductor in which the induced current is required to flow. Whatever, you have to turn it around for whatever reason. If a current is used, a so-called primary current, to set up an induced current in another coil called a secondary coil, the induced current only flows when the primary current starts or stops. This starting and stopping of a current is not instantaneous. There is a small period of time during which a current grows to its maximum value and then grows less. During this period of time, the magnetic field associated with the current also grows and decays. It is this movement of the magnetic field which is capable of establishing an induced current. Obviously, what is wanted for practical purpose here is a current which starts and stops many times each second. Such a current is called an alternating current. Usually such a current has the form of a sine wave. The current flows first in one direction, growing to a maximum value and decays to zero before growing to a maximum in the opposite direction. The current goes to and fro, and such a current is what is required for a transformator which involves electromagnetic induction. We can follow the basic principles. And at that moment when we just read the thing about the magnetic field, we understood that we're bending the thing. Normally you bend it, and if the outside there's a magnetic field, you have no magnet. So you have a bar of iron, coil around, a wire around it with a current on it. When an electromagnetic field is established here, you have here a magnet, and here. You bend the thing, you have a here and here, and you can use both ends together. If you have now something big like that, and that whole magnetic field reaches just inside of this book, if it would be magnet permeable or whatever it calls, then it would be even without poles. That means he understood basically what we wanted to understand, what they wanted us to tell there in that part by reading it a second time, and also hear a little bit more. That means we can follow, and it seems if we read something for the second time, we understand more. That means that was the electrical engineering part. If you were here for electrical engineering, you can go directly to the next part of electrical engineering. If you were here extensor couple nurse training, I'm sorry we don't have time left. Thank you very much, and